Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section we're going to tackle everyone's favorite topic, and that is partial fractions expansion, the technique of integration involving partial fractions expansion. Most people don't like this section of calculus mainly because it's very tedious. Okay, it's very tedious. There's a lot of algebra involved. Okay, you're trying to do something to make the integrals simpler so that you can solve them. That's what the whole point of it is. But in order to get there, in order to actually do that, you usually have quite a bit of algebra and quite a bit of steps. And that usually introduces a lot of chance for errors, simple errors usually, very simple sign errors. And you're tracing back through 2 pages of work trying to find out where you made your mistake, and it was a sign error back on the 16th step way up on the previous page. Okay, the only thing I can tell you there is just take your math one step at a time and check every line before going on to the next one and make sure everything you're doing is right. It just comes with practice, and heck, I make mistakes all the time, so it's not like we don't all make mistakes. All right, partial fractions expansion, what is it? Let's say, I'm going to show you by example why you would want to do this. Let's say you want to do the integral 3x plus 1 over x squared plus x dx. Well, anytime you're given an integral, the first thing you want to see is if you can do a simple substitution. But I don't think you're going to find one here, because if you substitute in for x squared and you take the derivative, you'll get 2x, and that's not going to cancel anything. If you substitute in x squared plus x, you'll take the derivative of that, you'll get 2x plus 1. That doesn't cancel with what you have on the top. So no quick and dirty substitution is really going to help you here. So you're kind of stuck. This is fairly difficult. So what if I told you, though, what if I told you that this integral could be magically transformed into the following? Now, I'm not even going to show you why yet. I'm just going to say, what if it could be broken down into this? Okay, if I could show you a way to magically take this integral and break it into this, you can integrate that. Because here you have the integral of the sum of 2 things, which is just the integral of the first thing plus the integral of the second thing. This thing, integral, is just the natural log of x, and the integral of this thing can be done by a quick substitution, because if you take u and substitute x plus 1, take the derivative of that, you'll just get the derivative, which is 1. And when you do all of this, I think you can convince yourself you can integrate this, and you can integrate this. So you can do this. So the trick is finding out how to change a what you call a rational expression that has a polynomial on the top and a polynomial on the bottom. How do you systematically, in a bulletproof way, turn these functions, these rational functions, into partial fraction expansions? That's the trick. I mean, if you can do that, you can change the world, and you can definitely do it. Okay. Now, one more thing I want to show you real quick, just to kind of prove to you that this is the case, is if you have 1 over x plus 2 over x plus 1, and I wanted to add them together to see what I get, how would I do that? Well, I could take 1 over x, and I can multiply him by a conversion factor, x plus 1 over x plus 1, because I'm trying to form a common denominator here. And then I can take the second piece, this piece, 2 over x plus 1, and I can multiply him by x over x. And the reason I'm doing this, by the way, is I'm multiplying by 1 here, so I've changed nothing. I'm multiplying by 1 here, so I've changed nothing. But in the end, what I'm trying to do is I'm trying to get a common denominator. X plus 1 over here over x times x plus 1. And then on this side, it's 2x on the top, and then x and x plus 1 on the bottom. And the reason I did that is because on the top, when you add these fractions, now that I have a common denominator, you'll have 2x plus x plus 1 over x times x plus 1, denominator stays the same, and on the top you'll have 3x plus 1 over x squared plus x. So I'm just showing you by reverse engineering this problem that these 2 fractions, when you add them together and you actually do the math, get a common denominator, add them together and simplify, it actually does equal this. So the remainder of this section is going to be showing you the bulletproof way to do that, how to take this rational expression, how to bust it apart into some simpler pieces, and do the integration. So these problems are going to be long, because the first part of the problem is going to be dealing with breaking it into the partial fractions, and then the next part of the problem is going to be integrating those little pieces, which would be like integrating these pieces. So you're going to generally have multiple integrals going on, and then you kind of throw it all together at the end. So they're probably going to take the whole board up and go from there. So what I'm going to do first is I'm going to I like to teach by example, okay, and that's what I plan to do in this section. But I need to kind of outline the process of partial fractions in a kind of a formal way. So I'm going to probably fill up the whole board just showing you the general, in all of its glory, partial fractions expansion method, because when you open your book, it's exactly what it's going to tell you, and I want to try to teach you how to understand your book. So I'm going to go through that, but then the rest of the time we're going to be working example after example to show you practically how to use it. And when you look at the book, your eyes might cross and they might glaze over because it's long-winded. But when you actually do the problems, it's really not that bad. Okay, so if you want to expand, I'm just going to write a note to you and to myself to expand something like, and this is something like, so it can actually be anything. This is just an example. X squared plus 2x over x cubed plus 4. That's a rational expression. You can have any polynomial on the top and any polynomial on the bottom. It's just going to get nastier and nastier, okay, to actually do the math. Okay, so here we go. Part A, step number 1, I guess you could say, okay? And I'm just going to write this down. If the degree of the numerator, and this is the numerator I'm talking about here, the degree is the highest power that you have, is greater than or equal to the degree of the denominator, perform long division. Okay, so basically an example of that would be if I told you, and if inside your integral you had something like x, so an example would be like x to the fourth plus 2x plus 3 over x squared plus 9. That would be an example where the degree of the numerator is greater than or equal to the degree of the denominator. In that case, you want to do long division, and what you're trying to do here is basically when you do your partial fractions expansion, you always want the degree of the numerator to be less than the degree of the denominator. That's just the way the procedure works. So most of the problems you'll have, it's already going to be like that, and you won't have to do this long division. But if the degree of the top is greater than the degree of the bottom, then you're going to need to pull out your rusty algebra tricks and do your long division, and so that you can actually divide into there, and in the end you will end up with a polynomial on the top with a degree less than on the bottom. So we'll do a problem like that to refresh your memory. So that's part A. Check the degree of the top and the bottom, and if the top is greater, then you do long division, and then whatever you get left over with after that division, then you proceed with the rest. Most of the time you won't have to do part A because most of the problems will not have a degree on the top that's greater. Okay, here's where the rubber meets the road. The next thing you do is you want to factor the numerator and denominator into expressions of the form, and here are the various expressions. I'm going to go ahead and change colors when I do this, just to break, because this is actually very, very important that you see this and it stands out from the board. You can factor them out into constants. You can factor them out into expressions of x minus a number. A is a number raised to the power of r. R is another number. So this would be like x minus 2 to the second power, x minus 3 to the third power, x minus 1 to the first power, so x minus 1, etc. Okay? And in this case, r is an integer, and a is also a constant. And the third way that third type of expression you want to try to factor it into, if you can, is x squared plus bx plus c to the power of s, where s is an integer. Okay. Now I need to stop and tell you here that This is the full-blown glory of partial fractions. Almost no problem you will ever actually have to do this, because you'll see quickly when we start working problems, if you get into an expression where you factor it into this form here, the problem gets ugly really quickly and it becomes just a boatload of algebra. So you really aren't going to have to do that much, but in the general sense, if you start factoring the top and factoring the bottom, and this is as far as you can go and you can't factor this anymore, then partial fractions can still take care of you. It's just going to take some work. Okay. So the next thing you want to do after you've factored, I mean, this is a bunch of words. Basically, you factor the top, you factor the bottom. You factor as much as you can. Okay. The next thing you want to do is you want to then cancel common factors in numerator and denominator. Okay, so you factor the top, you factor the bottom, you cancel terms, and whatever you're left with, you're gonna press on into the rest of the thing here. Okay, so review the bitting. If the degree of the top is greater than the bottom, you do long division. Most of the time it won't be. So A usually isn't applicable anyway. You get to B, you factor the top, you factor the bottom. I'm just giving you the forms in which, the legal forms that you try to factor them into. You cancel the common factors in the top and the bottom. Okay, now the next part is also very, very, very important. And what you do is you write the thing that you're trying to write as a partial fraction into the following forms. Write in following form. Okay, and I'm going to switch colors because this is very important. You're going to write your expression. This is the magic of it. You're going to write your expression as some number a1 over x minus a. Because remember, we factored it into the form of x minus a, plus a2, which is just another number, x minus a squared, plus dot 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 plus a sub 3 or 4 or 5 or however far you go, x minus a to the r. Okay, so basically, when you factor the bottom, okay, when you factor the bottom, you're gonna, and you said you're gonna factor into forms that look like this. If you get some x minus a to the power of 2, then in the final answer of what you're trying to expand it into, you're going to have an x minus a and x minus a squared. Okay? If you factor the bottom into, and you're going to have a term in the bottom that has x minus a to the 4th power, then you're going to have some number over x minus a, some number over x minus a squared, some number minus x, over x minus a cubed, and some number over x minus a to the 4th power. So whatever power you have in the bottom of x minus a, which is just a factor, you're going to have that many terms going up here. And they're all going to have constants. Now these numbers here on the top, these a's, these are the coefficients of your partial fraction expansion. Okay, now let's say you had some factors on the bottom that look like this. Then those would be written very, very similarly. The top would say b1x plus c 1 over x squared plus bx plus c, okay, plus b2x plus c2 over x squared plus bx plus c squared plus dot dot dot. Okay, so it's the same kind of thing. If you have factors on the bottom that look like this, because maybe you couldn't factor this anymore, then you're going to have one of these on the bottom, and you're not going to have a constant number on the top like you had up here. You're going to have bx plus c, bx plus c. So if you were unfortunate enough to have something on the bottom that had x squared plus bx, some polynomial raised to the power of 2 on the bottom, and that's as far as you could go factor-wise, then when you did your partial fractions breakup, you're going to have a term that has this on the bottom with bx plus c, and you're going to have a square term here, this guy squared, with some other constants, x plus c. Okay. Again, this is the general form. It's going to be much, much clearer once we get to doing some problems, but I need to go through this because you're going to see this in your book. Okay. Now, to continue on, we're going to move over here. Part D, you simply solve for the a's, b's, and c's. Okay, the a's, b's, and c's. And then the final thing is integrate each expression separately. That's what you're doing here. So here it is in a nutshell. Here it is in a nutshell. This is partial fractions expansion. If you could only get it to fit in this much space on your test paper, then you would be really happy, because it does get to be, you know, a little bit long is really what it comes down to. Well, let's go over it one more time, and then we'll work some problems and we'll get some practical work with it, and I think you'll feel a lot more comfortable about it. Okay, you're trying to expand something. It's a rational expression, has a polynomial on the top and a polynomial on the bottom. If in the original problem, the integrand, which is this ratio here, has a power on the top greater than the bottom, then you want to do long division, and we'll have a problem like that, and you'll see why. When you do your long division, you're gonna get a result that does not have a power in the top greater than the bottom, and that's what you want to have to press forward. Most of the problems will not be like that. Most of the problems will be more like this one, where the degree of the top is less than the bottom. In that case, you can just skip part A completely. So look, I've already eliminated 1 out of 5 steps for you, most of the time. The next thing you want to do is factor all of the expressions on the top and on the bottom and make any cancellations, and you can factor out constants. You can factor out, you see it's fancy looking here, x minus a to the r power. That's just simply like, you know, when you factor a polynomial, you might have x plus 5 times x minus 2. Okay, well, x plus 5 is of this form. R is just 1 in that case. X minus 3 is R is equal to 1 in that case. You can also factor, if you're doing factoring, you can have x minus 1 squared. You can have x plus 2 to the 4th. You can have things like this. So it's the general case. So you can factor into forms like this. You can also, sometimes, you know, you might get to the point where you have an x squared plus 2x plus 3, and you can't go anymore. You can't factor it, so you might be stuck with that. But you factor as much as you can, and you cancel from the top and the bottom. Whatever you're left with, that's what you're going to actually try to expand in partial fractions. Almost all the time you're going to be operating up here. This is generally not going to happen, but it's just shown here for completeness. So every factor you have in the form of x minus a, you'll write it with a constant on the top. Constant on the top. If you have a square term, then you'll have to write the same number of these things as you have in the exponent here. So if it was x minus 2 squared, then you'd have x minus 2 with a constant that you're going to have to solve for, x minus 2 squared with another constant, and so on and so forth. Okay? Then the next step is to solve for all the a's and b's and c's, and that is going to put numbers in these positions. Now remember, a is already given because you've already factored, you know, it's x minus 2 or x plus 4 or whatever it is, and then on the top is what you're trying to solve for, and then in the end, that's going to be your partial fractions expansion, and then you're going to have a sum of separate elements there, and you're going to have to integrate those separately, and you can usually do that. The integrals usually turn out to be pretty easy in these problems because you break them up in these little simple pieces. They're usually integrated pretty easily with substitution. Okay, so we've presented the procedure of partial fractions on the board. It's this abstract thing you'll see in your textbook, and it'll have a bunch of steps. Here we're going to do some problems. I think you'll see pretty quickly that it is a mechanical type of thing. Once you get started on them, you can have a mechanical way just to bang through them, and once you know that, then it's a very definite way to solve these kind of problems, and we'll do them here, and you'll see that it's really not that hard. Now what if you're going to integrate from 3 to 4, those are your limits of integration, the following: 5 over, and I'm going to write it as x minus 2 times x plus 3 dx. Well, the first step in the procedure, the very first step, was to see if the degree of the numerator is greater than the degree of the denominator. Now, if I multiply this, if I do FOIL and multiply this out, I'm going to have an x squared term on the bottom, and I don't have any x's up here. So right away I know I'm in good shape because the degree of the top is less than the degree of the bottom. And look right there, you've already eliminated one step. You don't have to do anything else with part A. You're done with that. Okay, now part B said to go ahead and factor the top and factor the bottom and cancel terms. Well, this problem actually already had it in factored form, so we don't even need to do that. We don't have to do any factoring or canceling because we're already done. Okay? So, what are we going to do next? We're going to try to partial fraction expansion this thing, and what we're trying to do here is we have 5 over x minus 2 times x plus 3. And the factors, remember I said in the other page there, it's x minus a to the r. You can have them of this form. This is what I was talking about. This is fancy math speak. This is a factor of this form. This is a factor of this form. It's just that r is equal to 1 in those cases. So these factors, the factors that you're so familiar with dealing with, are 99% of the time going to be the type that you're going to use in your partial fractions expansion. So the way you write it is a over this factor, x minus 2, plus b over this factor, x plus 3. Okay, that's what you're going to do. Now notice that in the previous board, when I showed you in all of its glory, I had a1 and a2 and a3 and a4, but those are just constants. I like to use a and b for my constants I'm trying to find in my partial fractions because it helps me keep it straight, and you know, if you have a bunch of subscripts running around, you can get confused. Okay, so now what you need to do when you think about it is all you have to do is find out what a is and find out what b is, and if you can do that, then you've done your expansion. You can integrate these pretty easily. Okay, so that's what we're going to do next. In order to solve for a and b, I'm going to multiply both sides of this equation because we're saying this is an equation. This is what it's equal to. Let's just have some unknowns here. I'm going to multiply both sides of the equation by this bottom part here. And that's going to cancel with this. It's going to make a cancellation here for me. It's going to make a cancellation here for me. So multiplying both sides by the entire denominator here, I'm going to have 5 is equal to a times x plus 3 plus b times x minus 2. Make sure you understand that. Multiplying by the whole bottom, this thing cancels on the bottom here. On the a, the x minus 2 cancels, leaving me with x plus 3. And on the b, the x plus 3 cancels, leaving me with x minus 2. Okay. Now, the thing that's really cool about this is you want to find out what a and b are. That's what your goal is. And then once you do that, you've done your partial fraction expansion. You can do your integration. This is an equation and it's valid for all values of x. All values, okay? So I can pick any values that are convenient to me and plug them in here to find out what a and b are, okay? So I notice right away I've got two convenient points here, okay? Let's say, let me write this in a different color just so it's clear. At x is equal to minus 3, because that's going to make this go to 0, then the equation will be 5 is equal to 0, right, because negative 3 plus 3 is 0, plus b times negative 3 minus 2. I'm just plugging in my value of x. I can pick any value of x, but this x is particularly nice because it chops through this thing here for me. Then what I'll have is 5 is equal to negative 5b, just doing this math here, so then b is equal to negative 1. b is equal to negative 1. So look, I found one of these pieces of this puzzle here, okay? Now, let's do the other one. At x is equal to 2, because I'm going to chop through this one. Then what you have for this equation is 5 is equal to a times 2 plus 3, plugging in 2 up here, plus 0, because if I plug in 2 here, I'm going to get 0. Now let's solve for a. Okay, so continuing our simplification here, we're going to have 5 is equal to 5a, and then a is going to equal to 1, dividing both sides by 5 here. Okay, and I found out something very important. I found out what a and b are. And I've done it by solving this equation and picking smart values of x. So basically anything in the parentheses here, you're just going to pick that value of x to make it go away, and then you're going to solve for the other variable. So I have found out what a is, and I have found out what b is. Okay, so I have done a large amount of work here, okay? So let's go ahead and move to the other side of the board, and let's go ahead and write that down. So my integral has now become, I have transformed my integral from 3 to 4. Okay, I have transformed this integral from 3 to 4. A was equal to 1, so it's going to be 1 over x minus 2. Okay, and b is negative 1, so I'm going to have minus 1 over x plus 3. Okay, dx. So I have transformed that original integral into a very simple integral, and I can actually evaluate that. So this is exactly how I write it on my paper when I do my problems, even today. When I have an integral of something minus or plus something else, and it's very easy to get really confused, especially if you're going to have to use substitution a couple of times, this is exactly what I do. I write some curly braces here, and I write a note to myself that I'm working on this integral right here. So then what I will do next is I will say u is equal to x minus 2, okay, because I'm just going to go ahead and do a quick substitution, du dx is equal to 1, taking the derivative of this is equal to 1, so then du is equal to dx. Okay, du is equal to dx. Why did I do that? Because this integral is going to be integral of 3 to 4 of 1 over u, and it's going to be dx, and dx we said was equal to du. Okay, so I did that so I could actually integrate this. Integral of 1 over u is equal to natural log of u plus, well, it's not plus a constant because it's a definite integral. We're evaluating it from 3 to 4. Now you have to be really careful here because when you do this integration, you've done it in terms of u, but your limits are in terms of x. So before we actually evaluate the limits of integration, I'm going to plug in for what I know u is, and u was equal to x minus 2, and I'm going to evaluate that from 3 to 4. Okay? So that's going to be natural log of 4 minus 2 is 2 minus natural log of 3 minus 2 is 1. Okay, so I just plugged in 4 in here and 3 in here and got that. And remember back a property of natural logarithms, natural log of a minus natural log of b is equal to natural log of a over b. I'm going to use that property here. Anytime you take the difference of logs, you just basically are dividing them. So I'm going to use that here to make this, stand out and make it simple. Okay, so that's going to be natural log of 2 over 1, just dividing them. And so it's natural log of 2. So you see, it's a lot of steps. I'm being excruciating about it myself, but really, this is a very simple integral to do, okay? And you could probably do it in fewer steps, but I chose to, and I always choose to show all the steps. So that is this integral. Now, this integral here, you have to be very careful because you have a negative sign, okay? Well, what I'm going to do is I'm going to say u is the same way. I'm going to say u is equal to x plus 3, so then du dx is equal to derivative of this, which is 1. Okay, derivative of x plus 3 is 1. So then dx is equal to du, just like before. And I'm going to go ahead and do my substitution. So I'm going to make sure I have my negative here. It's going to be negative integral from 3 to 4 of 1 over u du, because plugging in for dx is du. Okay, so that worked out really nice. So it's going to be negative natural log of u from 3 to 4. But again, that is in terms of u, and my limits are in terms of x. So before I do any evaluation, I need to go back and substitute in what I know u is. Negative natural log of x plus 3 evaluated at 3 up to 4. Okay? And then it's going to be the same old story, negative. I'm going to go ahead and keep that negative here outside for right now. So it's going to be natural log of x plus 3. 4 plus 3 is 7. Minus natural log of 3 plus 3 is 6. Okay? So I'm going to evaluate the top, and I'm going to evaluate at the bottom limit, and I get these guys, and then using the same property of logs, it's going to be natural log of 7 over 6, because natural log of this minus natural log of this is going to be 7 over 6, which is going to be negative natural log of 7 over 6. So you see, this integral turned out to be 2, and the other integral turned out to be negative 7 over 6, including the negative sign. So the answer is going to be equal to, the total answer is going to be equal to natural log of 2 minus natural log of 7 over 6. Natural log of 2 minus natural log of 7 over 6. And you could stop there, you could circle it there, but this is also a difference of 2 logarithms, you see. So you could actually further simplify this and say this is natural log of 2 over 7, 6, because it's a difference of 2 logs, this one divided by this guy right here. So this is going to equal natural log of taking this fraction, flipping it over, and multiplying, because you're dividing fractions. It's going to be 12 over 7. 2 times 6 is 12 over 7. So the final answer is natural log of 12 sevenths, and that's the answer. So, reviewing the bidding here, okay, we were given this expression. We knew we wanted to do partial fractions expansion. It was already factored, so all we did was we wrote a constant over one of the factors plus a constant over the other factor. We cross-multiplied through to get it in this form. We found a and b by choosing clever values of x. We found a and b. And then we moved over here and we plugged in a and b, and this is our partial fractions expansion, and then we just integrated the left with substitution, integrated the right with substitution, made sure to keep all of our signs tidy and add them together, and that is how you evaluate that integral. Okay, so the next problem is going to be a little bit more challenging. What if you had the integral of 3x over x squared minus 8x plus 15 dx, and you had to evaluate that integral? You know you're going to want to use partial fractions expansions, or you expect that you probably will. So the first thing you want to do is look at the degree of the top and the degree of the bottom. The degree of this one is less than the degree of that one, so you don't have to do that part A. You don't have to do any long division. You're good to go. So the next step says, let's go ahead and try to factor this thing. So the first part, the top, is already factored. I mean, there's nothing to factor there. So let's see if we can factor the bottom. Because it's x squared, I'm going to have x and x. And because it's 15, I'm probably going to use 3 times 5. Okay? And because it's a negative 8x, I probably need to put negative, negative. Negative 3 times negative 5 gives me positive 15. Inside's negative 3x. Outside is negative 5x. Add them together, I get my negative 8x. So that is the factored form. There's nothing to cancel. I can't really do any cancellation. That was also part of the method. And you see, this problem is also, now that we've gotten to this point, is very similar to the last problem. We have factors on the bottom that are of the form x minus a to the r. It's just that r is 1 in this case. So it's really simple, and most of the problems are going to be like that. It's just that when you look at that giant, massive technique on partial fractions, it's all inclusive and it's very general, and so it's hard to read. So what we want to do is we want to rewrite this integrand, this 3x over x minus 3 times x minus 5. We want to rewrite it, and we're going to rewrite it like this. Constant over one of the factors, x minus 3, plus another constant, b, separate constant, x minus 5. That's our goal. We want to write it in this form. And if we can do that, if we can find a and b, then we will have very easy integrals to evaluate. So the next thing we want to do is we cross multiply through by this denominator and get this thing looking tidy. So once we do that, on the left we'll have 3x is equal to, cross multiplying by the entire denominator, a times x minus 5 plus b times x minus 3. Take this entire thing and multiply it all the way through. I'm going to get cancellation in x minus 3. I'm going to get a cancellation in x minus 5. This is what I'm going to be left with. Now this equation, as we said before, is valid for all values of x. So I can pick cute, clever values of x to help me solve for a and b, and that's what I'm going to do here. So at x is equal to positive 5, that's going to make this drop to 0. Then I'm going to have 3 times 5 is equal to 0 because of this, plus b times 5 minus 3. Okay? So I'm going to have 15 is equal to 2b. Okay, 15 is equal to 2b. So then b is going to be equal to 15 divided by 2. Okay, so b is going to be 15 over 2. Now I can also pick another clever value at x is equal to positive 3, because that's going to kill this. The equation becomes 3 times 3 is equal to a times 3 minus 5 plus 0, because 3 minus 3 is 0. That drops out. 3 times 3 gives me 9. And a times 3 minus 5 is negative 2. So solving for a is equal to negative 9 halves. It's not a beautiful constant, but it is a constant, and we were able to find it. So we got two constants that are kind of ugly. They're fractions, but at least we found them. Okay? And we're half the battle. We've done the partial fractions expansion. Now we just have to go over there and write it down and solve. Okay? So, moving over here, we're going to write this integral as follows. Integral of a was given by negative 9 halves, so it's going to be negative 9 halves over the denominator x minus 3, okay, plus b, which was found to be 15 halves over x minus 5 dx. Okay, so that is what we have to do. And these are kind of ugly because of these constants, but they're really not that big of a deal, and they can be solved very simply like this. So what we're going to do is we're going to solve this integral first. So we're going to have negative integral let me write this as negative 9 halves times the integral 1 over x minus 3 dx. That's what this integral is equal to. I just pulled out the negative 9 halves, and I have the 1 over x minus 3 there. And then I'm going to use a quick substitution. U is equal to x minus 3. Du dx is equal to 1. Derivative of this is equal to 1. And then dx is equal to du. And that's going to let me substitute in negative 9 halves integral 1 over u du. And you guys may not all have to do this. I personally like to do the substitution just to make sure I haven't missed anything. Okay? Now when we do this, this is going to be negative 9 halves times the natural log of u, okay? Obviously plus a constant, okay? And u was given up here as x minus 3. Okay, so it's going to be negative 9 halves natural log of x minus 3 plus c. Okay, negative 9 halves natural log x minus 3 plus c. So that's this one, and then let's work on this one over here. Okay, I'm going to have 15 halves integral 1 over x minus 5 dx. That's the integral I'm working on, and it's kind of boring, but I'm going to do the same thing. U is equal to x minus 5 du dx is equal to 1, and then dx, which is what I'll need for the substitution, is equal to du. Now I can do the substitution. 15 halves times the integral of 1 over u, because in this case this u is x minus 5 there. Du, because dx is equal to du, and this is going to equal 15 halves times natural log of u plus a constant, and then u we already found from before. We actually decided that u was equal to x minus 5, natural log of x minus 5 plus a constant. So what we've done here is we found the first integral and we found the second integral, and the final answer is going to have them added together. So what we're going to have is, I'm going to start over here, 15 halves times the natural log of x minus 5 minus, because this is a minus here, 9 halves times the natural log of x minus 3 plus a constant. Now notice that when I did this little bitty integral here, I had a constant, and when I had this little bitty integral here, I had a constant. When I wrote my final answer down, I just have one constant. Well, it's an arbitrary constant, so one little constant plus one more little constant is just one constant. So when you write that all together, you'd only have to put one constant in there. So 15 halves natural log x minus 5 minus 9 halves natural log x minus 3. So reviewing what we've done on this problem, just to make sure we all have it, this is the integrand. We factored the bottom into this form here, and then we put constants over those factors. Okay, and then we cross-multiplied by the denominator, and we got this equation here, and we chose clever values for x so that we could solve for a and b. Once we had a and b, we plugged them in to our form for the partial fraction. This is our partial fraction expansion right here, and then we just did quick substitution integration on each side and got two little answers, and made sure to add those up. Okay, now in the next problem we're going to tackle our first problem where we're actually going to have to do that long division. So let's just jump right on into it. Let's say you had to do the problem integration of x squared over x plus 1 dx. So the first thing we have to do is look at the degree of the top, which is 2, and the degree of the bottom, which is 1, and the degree of top is greater. So we're going to have to do this long division thing, which we hadn't had to do before, and now you'll see why. So remember, any fraction is just a division. This is x squared divided by x plus 1. Okay, so we're going to do that right over here. We're going to do it right over here, and we're going to do it in red. We're going to say you have x squared, and we're dividing by x plus 1, which is exactly what we're doing. X squared divided by x plus 1. Okay, now one thing you have to look at is, even though it's x squared, this is really x squared plus 0x plus 0, because you have to fill in all the blanks for this polynomial, 0x and then 0 for the constant. Okay, now here's how you do long division. You look only at the x and you see how many times it can go into x squared. How many times can x go into x squared? Well, the answer is it can go x times, because x times x is x squared. You don't look at the 1, you don't look at this other stuff, you just look at x and how many times it can go into x squared. It can go x times because x times x is x squared. So do this multiplication. X times x is x squared. X times 1 is x. Okay? And because these are added together, you have a plus here, and so this is what you're going to have right there. And now, just like you do in regular division, you're going to do a subtraction. X squared minus x squared is 0, and 0x minus x is negative x. Okay, so you have negative x there. Okay, so now that you have this done to this point, you need to ask yourself, how many times will x go into negative x? And the answer is negative 1 time. Because negative 1 times x is negative x. Okay, so you write that down there. Don't forget to multiply by the other part. Negative 1 times 1 is negative 1. And then you want to go ahead and do a subtraction again. Negative x minus negative x is same thing as negative x plus x, which is 0. Okay, and then you have 0 minus negative 1 is 1. Positive 1. So what you have here is positive 1 being a remainder, you see, because there's nothing else you can do. There's nothing else you can do here. You've already gone, you can't divide this into here. You could try, x goes into 1 0 times, and you could put a 0 up here, but it isn't really going to help you with anything. So what you have done is you've done long division, and you found that x plus 1 can be divided into this thing x plus 1 times, but you have a remainder. Okay. Now let me refresh your memory back from 3rd grade math. When you have 9 and divide by 4, okay, you know right away that that can go 2 times, right, because 2 times 4 is 8, okay, but there's a remainder there. The remainder is 1 because 2 times 4 is 8, and there's a difference between 8 and 9 of 1, right? So there's 2 ways to represent this. You can say 4 goes into 9 2 times with a remainder of 1, okay, or you can say 4 goes into 9 2 and 1/4 times. Okay, so you can take your remainder and put it over what you divided by and say this is what it has, 2 1/4 times. 4 goes into 9 2 whole times plus another 1/4 of a time. Okay, so that's sort of another way you can write the remainder, and we're gonna use that here. So this division basically says that what it says, and I'll come back over here and write it right here, is it says that x squared over x plus 1 equals, because we've done the long division, it equals x minus 1 with the remainder of 1 over x plus 1. And that's exactly what I showed you with the other thing, with the dividing 4 into 9. You had a remainder of 1, and you put it over what you were dividing by, and that was what you had there. So here you did the division. It went x plus 1 times with a remainder of 1 over what you divided by. Okay, so is this helpful? Well, you tell me, do you think it's helpful? Well, what we have here, remember what we're doing is we're integrating this. So what we have here is this, and let's say we tried to integrate this. Let's say we went ahead and tried to do it. Integration of x minus 1 plus, and you can just put parentheses around it, that's fine, 1 over x plus 1 dx. Now look here, we actually didn't even have to do any partial fractions. All we did was do the division, okay? And when we did the division, this as a term is easy to integrate because this is just a simple polynomial, right? And this is pretty simple to integrate too with substitution. So we can actually do the integration without even doing any partial fractions. So the integral of x minus 1 dx is simply equal to 1/2 x squared. Integration of x is 1/2 x squared, okay, minus x plus a constant, because integration of 1 is going to give you the x. This is your basic integration of polynomials, okay? So that's going to be that one. And this one right here is going to be, I'm going to do it over here, integration of 1 over x plus 1 dx, okay? And here I'm going to use a substitution. U is equal to x plus 1, du dx is equal to 1, so then du is equal to dx, and I can plug that in here and say u is equal to, our integral is 1 over u, because x plus 1 is u, dx we defined as du, so I'm just doing a quick substitution so that I can put my mind at ease that I didn't actually screw anything up here, and say the integral of this is natural log of u plus a constant, and then we just go back and substitute what we had for u, x plus 1 plus a constant. So we have 2 little things here from our little mini integrals And so the final answer is going to be 1/2 x squared minus x plus natural log of x plus 1 plus a constant. It's a pretty complicated answer. I mean, I don't think you'd get there without doing partial fractions expansion. Now, we didn't actually have to do the partial fractions at all in this case. That's kind of why I did this problem, to show you that. First thing you want to do is do the division. We did the division here, give you some practice with the long division. We wrote it as what we divided, what we got as an answer plus a remainder. And when we did that, we looked and we said, well, geez, there's nothing more to do. I can integrate this. And you just integrate each little part just like that. Okay, now the next problem is integral of 3x over x minus 2 squared dx. And the first thing you want to do is you want to look at this and say, do I need to do any division? Well, the degree of the top is 1, and the degree of the bottom, if you were to expand this out, is just going to be an x squared. So the degree of the top is less than the bottom, so I think you're okay. So you want to expand 3x over x minus 2 squared. There's nothing really to factor here because it's already really done, but notice that this is of the form x minus a to the r, where r is 2 in this case. R is r squared, okay? So when you do this, you're going to have a constant over x minus 2, but you're going to have another constant over x minus 2 squared. That's what I was trying to say before in the very first part when I was introducing the whole partial fractions thing. If you have a factor with a power here, you have to have a term in the partial fractions expansion to cover every power leading up to what you had. So here it was x squared. I had a x minus 2 and an x minus 2 squared. If it were x minus 2 cubed, I'd have x minus 2 squared, x minus 2 cubed, all with a constant on top. So that's what I meant by that. So that's the only wrinkle in this, is just knowing that, and then the rest of the math is really all the same. So next thing we do is we multiply by this denominator to simplify this. 3x is equal to a times x minus 2 plus b, because x minus 2 is going to cancel completely when we multiply it all out. Okay, now let's choose our clever values here. At x is equal to 2, okay, I have 3 times 2 is equal to 0. 2 minus 2 is 0, plus b. So I have b is equal to 6, so that's important. b is equal to 6. Now, this one's a little bit different because I don't have another value of x that I can plug in here that I can do. So the next best thing in that case is I'm just going to plug in what I know for b and see if I can find out what a is. 3x is equal to a times x minus 2 plus 6. Okay, now the question is, how do I find a? I need to find a. I can't pick another clever value of x to help me do that. I've already used that trick. So let me show you one more trick, and you're going to need to know this for your problems. I'm going to go ahead and distribute this a in. It's going to be ax minus 2a plus 6. Okay, now look at what I have here. This is an equation valid for all values of x. I have an x term with a 3 in front, and I have an x term over here with an a in front. Now these other things, they have an a and a 6, but this is just a constant, because remember, a is just a constant. I don't know what it is yet. This is a constant term, okay? And over here, this is a term in front of x, and this is a term in front of x. So if this equation is actually going to be valid, I know that a must be equal to 3. Because what I do is I look at the coefficient in front of the x and I say I set it equal to the coefficient in front of this x over here, and it has to be true. That's the only way this equation can be valid. So I know that a is equal to 3 and b is equal to 6, and that is my partial fractions expansion. Okay, so the next thing we're going to do is actually do the integration. What we're going to do is we're going to say now our integral has changed to a, which is 3, over x minus 2, plus b, which is 6, over x minus 2 squared dx. So we've done our partial fractions expansion, and that's what it is. So I'm going to go and tackle this integral first, and I'm going to say u is equal to x minus 2, du dx is equal to 1. Taking the derivative of this is just 1. Okay? And then dx is equal to du, and now I'm going to go ahead and do the integration. integral of 3 over u, because x minus 2 is u, times dx, but dx is du, okay, is just simply going to be equal to 3 times the integral of 1 over u du. Just pulling out the 3, which is going to be natural log of u plus a constant, and then we just plug in what we know for u. 3 times x minus, it's going to be 3 times natural log of x minus 2 plus a constant. 3 times natural log of x minus 2 plus a constant. Now I'm going to work with this integral, which is a little bit more complicated, but not that much more complicated. I'm going to do the same thing. U is equal to x minus 2. Okay, same old story. Du dx is equal to 1, so then dx is equal to du. Now let's do the integration. Integration of 6 over u squared, because u in here is u squared, okay, times dx, but dx is equal to du, so I just put it down here. Okay, so I'm going to take the 6 out, 6 times integral, and this is 1 over u squared, and I'm going to write it as u to the negative 2, because I just like to do that with my polynomials. I like to have them up even if they have a negative exponent, because when I do the integration, it's going to be 6 over 1 plus the exponent. Negative 2 plus 1 is negative 1. So over 1 plus the exponent, u to the 1 plus the exponent, which is negative 1, plus a constant. So it's going to be negative 6. Okay, now I can bring my u back down to the bottom, and u is equal to x minus 2. X minus 2. So make sure you understand what I did here. I just said negative 6 because of the negative here. I take my u and I moved it down below again, and I substituted in x minus 2. And so those are my things here, and then I just need to add them together. So it's going to be 3 times the natural log of x minus 2 minus 6 over x minus 2 plus a constant. This is the answer to the integration. So just to make sure that we're all on the same page and do a little bit of review, we had an equation like this, an integral to do like this, and we did not have to do any division because the degree of the top was less. So then what we did is this was kind of already factored for us, and we know that when we have it in the form of x minus a number, we need to have things that look like that in the partial fraction expansion. We have to have the appropriate powers. So we did that, we cross multiplied through, got a simple equation, chose the clever value here and solved for b, but we couldn't do that twice because we didn't have anything here. So what we did next is we just plugged in for b, and we got this equation, we plugged in for b, and then we expanded and collect the terms of x and set them equal to the terms of x on the other side of the equation and found that a was equal to 3. Then we plugged in the values of a and b into the partial fraction expansion, did a quick substitution for that integral, a quick substitution for the other integral, and got the answer. So these problems so far you can see are not, well, I mean the first time you learn partial fractions it is a little bit daunting, but you can see it's mechanical. You crank through it. It's just that there's a lot of opportunity to make an error. That's the real problem. Okay, so the final problem is going to be integral of x squared plus 1 over x squared minus x dx. Okay? And what I want to do here is I want to figure out, first of all, the degree of the top is 2 and the degree of bottom is 2. And if you look back, you can't have that. You have to have the degree of the top less than. So you're going to have to do the division here, so we're going to get a little bit of practice here. Now what we're going to do now is do this long division, and so what we have is we have x squared plus 1 divided by x squared minus x. So we have x squared plus 1, but we want to write it as x squared plus 0x plus 1. When you do your division, you really need to put in zeros everywhere where there isn't a term. Okay? And you want to divide by x squared minus x. Okay? So the only thing we changed here was we put a 0 in front of the x because there is no x in that guy right there, so we just have to fill it up. Now look at the first term here and compare it to this one. X squared can go into x squared how many times? 1 time. Okay, it can go 1 time. So we'll go ahead and multiply and carry it down. 1 times x squared is x squared. 1 times negative x is negative x. And we're going to subtract these. Okay? X squared minus x squared is 0. And 0 minus negative x, because this is subtraction here, minus negative x is positive x. Okay? Okay, so you do the subtraction, And when you do the subtraction, you get x down here, and the next thing you want to do is drop down the next digit that you have. It's one of the things you do in long division. So we're going to drop down a +1. I'm going to go ahead and erase this because 0 really doesn't mean anything. And you have x plus 1 there. And now you want to see, does this go into here? Does x squared go into x? And it doesn't. It goes 0 times. So you could put 0 here if you want. And you'd multiply through and you'd get 0. And you subtract and you'd get x plus 1. And you do it again and again. And you wouldn't get anything else. So you're not going to have anything else up here. You're just going to have zeros. So what you have found is that x squared minus x divides into this one time with a remainder of x plus 1. Okay, with a remainder of x plus 1. And if you remember, the way we're going to write that is as follows. You write that as x squared plus 1 over x squared minus x is equal to 1, because we're doing that division, 1 plus our remainder, x plus 1 over what we divided by, x squared minus x. And that's, if you look a couple of examples ago, I showed you why that's the case, and that's analogous to the regular division you do today. So this is what you have here, and notice that you have a 1, and this is what you have to integrate here. This is what's under the integral. So integration of 1 is really easy, and the integration of this, notice now that you have a power in the top less than in the bottom, so you can actually do partial fractions on that, no problem at all. Okay, so let's work with this one right now. We're going to work with this one, and we're going to go ahead and erase what we had over here because we're going to need the space, and we're going to do the partial fraction expansion of this. We haven't forgotten about the 1. We know we still have to integrate that guy, but first let's do the partial fraction expansion of this. So, next thing I'm going to do is I'm going to say x plus 1 over x squared minus x is equal to, I'm going to factor x plus 1 over x times x minus 1. Okay, nothing cancels, so I have x times x minus 1. And I've got nice little factors here, so I know that that's going to be equal to a over x, this is one of the factors, plus b over the other factor, x minus 1. Okay? So that's what the partial fraction expansion is going to look like, so I'm going to now multiply by the denominator and go ahead and solve for a and b. So I'm going to have x plus 1 on the top is equal to a times x minus 1 plus b times x. Because multiplying by the denominator gives me some cancellation here with x, giving me x plus 1, and the other cancellation over here. Okay, so now the question is, let me go ahead and choose some cute values of x that help me solve for a and b. So at x is equal to 1, when this dry goes to 0, I'm going to have 1 plus 1 is equal to 0 right here, plus b times 1. So I'm going to have b is equal to 2 right here. b is equal to 2. And what else can I choose? I can choose x is equal to 0. That'll make this drop out. At x is equal to 0, I'm going to have 0 plus 1 on the left is equal to a times 0 minus 1 here, plus 0. So I'm going to have 1 is equal to negative a right here. So I'm going to have a is equal to negative 1. So I found a is equal to negative 1, a is equal to negative 1, and b is equal to 2. Okay? So what I'm going to do next is I'm going to go ahead and do those integrations. I'm going to move right on over here to the other side of the board, and I'm going to plug in what I know for a and what I know for b, and I'm going to do these integrations. So what I have here is the full integral. Okay, coming back over here, this is what we had to start with. We did the division, we got this plus this stuff, and we did a partial fraction on this. So the total integral is now going to be the integral of 1 plus a was given by negative 1, so it's going to be negative 1 over x. So I'm actually going to write that as negative 1 over x, okay, plus b was 2 over x minus 1 dx. So that's the integral in all of its glory. You've got 1, you've got a over x, 1 over x rather, and then you've got 2 over x minus 1. And you can do these integrals. These aren't that difficult. So this integral, and that's really easy. That the integral of 1 is just x plus constant, right? The integral of this guy, okay, the integral of this guy is going to be natural log of x plus a constant, because the integral of 1 over x is that. And then this guy I always like to do my substitution just to be rigorous. U is equal to x minus 1. du dx is equal to 1. Then dx is equal to du. So we go ahead and plug in. We've got integral of 2 over u, because that's what we did for our substitution, times dx, which was equal to du. So it's going to be equal to 2 times the natural log of u. Integral of 1 over u is natural log, plus a constant, and then we just plug in what we know for u, which is x minus 1. Natural log of x minus 1 plus a constant. Okay, so here we have the integral of this, the integral of this, and the integral of this, and now we can just put it all together. Total answer is going to be x minus natural log of x. Never forget your signs, okay? Plus 2 times natural log of x minus 1 plus a constant. This is the final answer. We just did our different parts here. So it was x minus natural log of x plus 2 times natural log of x minus 1 plus a constant. So let's review really quickly here. We had a function that we knew we had to divide because the degree of the top was the same as the bottom, so we did the division, and I erased it already, but the division showed us that it went one time plus a remainder, and we wrote the remainder over what we were dividing by. Okay, and then we chose to do partial fractions on this, so we factored this. We had a factor in x and a factor in x minus 1, so we put constants on the top. We cross-multiplied by the denominator, and when we did that, we had this simpler form of the equation here. We chose x is equal to 1 to find this. We chose x is equal to 0 to find the other. Those were our constants that we then put into the partial fractions expansion, not forgetting the fact that we still had to integrate the 1. Integration of the 1 was a simple x. Integration of 1 over x was natural log, and the integration of this also became a natural log with a little substitution. Make sure and add them all together and keep your signs straight, and we were good to go. So partial fractions is what we tackled in this class. Gives people a lot of problems, including me when I first learned it, and the reason is just simply because it's tedious. You are doing the partial fractions, you're solving equations. Sometimes with the more complicated ones you have simultaneous equations you have to solve. Sometimes you have to collect the x terms together to find out what the coefficients are. And then when you finally get that done and you do the actual partial fractions part of it, you put it all together, and now you have 3 integrals to solve. And you have to make sure and solve them all correctly, sometimes with substitution, and you have to make sure you have all the signs right, and then you put it all together and get an answer. So it's challenging, but it's mainly challenging because there's so many opportunities to introduce a sign error, and you really just need to do your best you can, step by step, and checking your work as you go, and don't do this stuff when you're really tired late at night either, because you make a lot of errors when you do that too. So that's how you tackle partial fraction expansions as a technique for integration.